Okay, so if we're given something like a mass spectrum like this, and we're asked to calculate the atomic mass of something, we're going to use our standard formula, and we take our mass charge ratio times its percentage abundance and add those all together and then divide by 100, because our overall total of percentage adds up to 100. So in this question, for us to calculate our atomic mass, we look at our first one and we take the mass of 90 times its percentage of 51.5 plus the next one of 91 times its percentage of 11.2 plus the next one, which is going to be 17.1% times our 92 plus our next one, which is 94 times 17.4 plus the last one, which is then 96 times 2.8. Okay, so those are all of our masses times each percentage, and we take that whole thing and divide it by 100. And if you type that whole sum into your calculator, you end up with your answer of 91.3 for the atomic mass. Okay, so that one is nice and straightforward, but sometimes instead of asking you to calculate the atomic mass, what they do is they give you the atomic mass and they ask you to calculate either the isotope mass in terms of this mass charge ratio or a percentage abundance. So if we look at this next example, so I have all my different isotopic masses for all the different isotopes and the percentage abundance of each, except for this last one is missing. And they ask you to calculate the isotopic mass of this last one after we're given the atomic mass of the sample. So we use the same formula again. So you're going to have your atomic mass equal to each specific mass times its percentage abundance, added together, all divided by 100. But this time we're given the atomic mass. So that value there of 140.116 is going to equal each of those times its percentage abundance, added to the next one, added to the next one, and now we get to the last one. So now the last one we're missing, but this percentage abundance must add up to 100 because we know you get a total of 100%. So we can find this percentage by saying 100 minus each of these percentages. So minus my 88.450 minus the 0.251 and then minus the 0.185, and if you type that into your calculator you get an answer of 11.114. So now that's this percentage over here, and now I still need to find the mass. So over here, where I'm normally timesing my percentages by my masses, I can take that percentage that I just worked out, and then I times it by my missing one, which I can then call x. And I put that whole sum over 100, just like my normal formula. And now I have an equation that I can solve for x. So to solve for x, I'm going to take my 100 to that side and multiply it. So I end up with 14011.6 equals, if I take all of my brackets multiplied and added together, I'll get a final answer of 12434.35165 plus my missing value of 11.114x. So now I can take this to this side by subtracting it, and if I take that minus that, I get an answer of 1577.24335 equals to my 11.114x. And then to solve for x, I'm just going to take this value divided by my 11.5 to get a value of x alone as 141.915. So this is then my isotopic mass that I was looking for, and I found the percentage abundance. So we can always find anything if we're given enough information, like this one. And then the other way, instead of asking you to find the isotopic mass now, to find the percentage abundance, so if I look at an example like this, I have mass spectrum giving our masses of 113 and 115, and I'm told my overall relative atomic mass is 114.5. And now they want us to find the relative abundances of our two isotopes. So we need that percentage abundance. So I've got two different isotopes. So I know that that percentage adds up to 100. So that means that what I can do is I can find by using x values. So I can say for this one, my percentage abundance would be x. That means for this one, the percentage abundance would be 100 minus x, because the total of them must add up to 100. So if I use those and my normal formula, I take my atomic mass of 114.5, put it equal to my isotope mass times its percentage abundance, which I now say is going to be x, plus the next mass times its percentage abundance, which I'm going to say is going to be 100 minus x now, all over 100. And now I have my equation and I can solve for x. So I can take the 100 to that side and multiply it to have 11450 going to equal to 113x plus 115 times 100, which is going to give me 11500, and then 115 times minus x. So that's going to be minus 115x as my equation. So now to solve for x, to get rid of the minus, if I switch that with that, I'll say 115x equals 113x plus 11500 minus my 11450. I can take this x to that side to get them all my x's on one side, so I say 115x minus 113x equals that minus that, which will give me an answer of 50. So now I'm left with 2x equals 50. So x alone is going to be 25, because I take the 50 divided by the 2. So that means the percentage abundance for the 113 mass is going to be my value for x, which is 25%. For the 115, it's going to be the 100 minus my value of x of 25, which will equal a percentage of 75. So as long as we can make one thing x, we can always solve for anything given our information in those different ways with our atomic masses.